everyone. My name is Afonso Villalonga and I'm a PhD student at Nova University of Lisbon in Portugal, advised by Professor Henrique Domingos and Professor João Rezende. The work that I'll be presenting is titled Looking at the Clouds, Leveraging Pub/Sub-Cloud Services for Censorship-Resistant Rendezvous Channels. So, to understand our work and the problem we are tackling, we have to go back and look at the basics and understand how most censorship evasion systems work. I promise this will make sense later on throughout the presentation. Typically, a user in a censored region establishes a covered channel or some sort of connection to a server, proxy, or entry node. And we will borrow the term bridge from Tor to denote any server, entry node, or proxy as a bridge. So, through this bridge, the user can access the censored content. So, all good, right? No problem with this model. Well, not entirely. The censor might realize that the server the user is accessing is actually a bridge for a censorship evasion system, and that the user is sending some sort of covert traffic, and because of this, block the bridge. So, one solution to this problem is just replacing the old blocked bridge with a new bridge. However, this has two main problems. So first, how do we send the new bridge information to the user since its old bridge is now blocked, and we assume that the user has no access to uncensored content? And second, if we replace the old bridge with a new one, how can we be sure that the new bridge will not fall into the hands of the censor? So this is all known in this is known in the literature as an enumeration attack, when a censor tries to block all the public bridges or all bridges that he finds online or in some sort of way. So the problem that I just described is typically called the bridge distribution problem. And in our paper, we have divided it into two adjacent sub-problems. So the first is how can we exchange the necessary information between the new bridge and the user so that the communication channel used by the user has a low risk of getting blocked. And the second is how can we ensure that the new bridge information or the new bridge does not fall into the hands of the censor. Our work is particularly focused on the first sub-problem. So, some existing solutions focus on using public mediums, like public forums, or messaging applications and emails as communication channels, to allow the user to obtain the new bridge information. However, each solution has its own problems. First, when using a public medium, such a public forum, censors could simply block the public medium being used and thereby prevent access to new bridge information. And second, both solutions require the user to manually configure the received information. This is particularly bad for censorship evasion systems that require more information than just IPs to establish a covert channel between the user and the bridge, which is the case to Snowflake and Tor Chameleon. So, a different way of solving this problem is by using what is called signaling channels or rendezvous channels. And the basic idea behind using this type of solution involves the user contacting a broker, which is a server that stores is a special server that stores bridge information, and that will help establish the connection between the user and the bridge, or contacting the bridge directly through a communication channel known as the rendezvous channel. The key property of rendezvous channels should be that they are difficult to block. So, what does it mean to be difficult to block? Well, we consider unblockability as a function that takes a service, protocol, or application as input and classifies it as either a good candidate or a bad candidate. So essentially, whether something is considered a good or bad candidate depends on various variables, particularly the sensor's capabilities and motivations, which might be linked to the application, protocol, or service being evaluated, and its tolerance to collateral damage. So the challenge lies in the fact that most of these variables can vary to some extent depending on the sensor, making it difficult to precisely estimate the overall unblockability of the service, protocol, or application being leveraged and evaluated. So, with this in mind, we searched for what are generally considered good candidates for rendezvous channels. Specifically, we focused on cloud services that would be suitable for our problem. We found the Google PubSub service. So the basic idea of Google PubSub, or any PubSub service for that matter, is as follows. There are publishers and subscribers. Publishers send message to specific topics, and subscribers receive message from topics they are subscribed to. This creates one-to-many communication channels where a publisher publishes message to possible multiple subscribers. Messages are exchanged using the Google PubSub API endpoint, which is listed down here. So, looking now back to our original first subproblem, where we need to exchange the necessary information to establish a connection between new bridges and users. Now, when the user wants to establish a connection to a new bridge, they execute our protocol by sending through the PubSub API messages to the broker and receive the corresponding responses. So once the exchange is complete, the connection is established. Now I'm going to explain in more detail our protocol. So the broker publishes message to BT topics, broker topic, and receives message via the UT topic, user topic. The user has the opposite configuration. It publishes message to the UT topic and receives messages from the BT topic. And these topics are created when the system is configured for the first time. So when the broker is set up for the first time, we also need to create a special subscription for the UT topic so that it can obtain the messages published by users. So this subscription remains active as long as the broker is operational. Next, the user sends a request to initiate the protocol and generates a session identifier that is randomly generated each time the user initiates the protocol. The broker responds. So the broker now responds with its public key. The user can use this public key to encrypt a newly generated symmetric key for the session and sends the encrypted symmetric key to the broker. The broker then waits to find an available bridge for the user and sends a notification once a bridge is located. The user and broker exchange the necessary information to establish a connection, and this information is encrypted using the established symmetric key. Finally, the bridge and the user establish the connection and can now exchange covered traffic. So, as a final note, this protocol is generic, so in theory, it can be applied to any PubSub service from any other cloud provider. Now, to block our system, the sensor would need to either block the entire Google Cloud platform, so like all Google Cloud services, or specifically target and block our PubSub service. So this is something that has happened in the past. So for example, China has Google Cloud blocked. However, we argue that it's still worthwhile to leverage services and protocols that might only work in some countries that experience censorship. Now, regarding testing, we tested the performance of our Rendezvous channel or system by deploying it with Tor Chameleon, which is basically a Tor pluggable transport that we also developed that encapsulates Tor traffic within WebRTC video frames from video streams, and therefore requires a signaling protocol to establish the WebRTC peer-to-peer connection between the bridge and the user via a signaling server. So we replaced the signaling server with the broker, which acts as a signaling server in this configuration, and use our developed system to exchange the necessary information for the connection between the user and the bridge. Here are the preliminary results we obtained. So the baseline is a default Tor Chameleon version. In the second row represents Tor Chameleon with our rendezvous channel. The first column indicates the time between the first message sent and the establishment of the covered channel. And the second column is specific to the rendezvous system and is basically the time it takes to create a subscription for the user. We can observe that the total time falls within reasonable values for bootstrapping Tor Chameleon, around 8 seconds. So finally, for future work, there is still much to be done, and most of what I've been presenting here is preliminary. We aim to conduct a more comprehensive experimental analysis focusing on both traffic fingerprinting and performance. Additionally, we plan to develop a defense for DDoS prevention within our system, which might become a problem if this ever gets implemented in the real world. Furthermore, we intend to explore possible solutions for the second sub-problem and integrate them into our system. And finally, although we implemented our system using the Google Pub Sub service, the protocol is theoretically generic enough to be implemented in other Pub Sub services, in other cloud providers, and is also something that we want to explore in the future. So that's it. Thank you so much for your time, and I leave here my contact information.
Thank you very much. Are there any questions? Yes, David.
Thanks. I like the way that you have broken down the bridge distribution problem into 2 sub-problems. I think that's very sensible. Interesting difference between this pub subsystem and the previous talk based on SQS. SQS had a dedicated downstream channel for every new request. So there was a global write channel, but then everyone has a dedicated read channel. This is different if I understand it correctly. Yes. Every client user, they're sort of sharing the same broadcast downstream channel, and they're seeing each other's messages. I think that's interesting, right? It's a kind of a different problem space. My question is, it seems like it's simpler to have dedicated downstreams. Does that just not generalize for the types of systems you're targeting?
So in our paper, we actually have, let me just pull the protocol.
Yeah,
so
exactly.
We have an alternative version of this protocol where we have single downstream channels for each user. Basically, what we do instead of this is have each broker create a specific topic that will be configured specifically for that user, for the user that is contacting the broker. So this is also an option. We have not implemented that, so we are not sure if it is possible. It should be in theory. I don't see any reason for not to be. So yeah, it's something that we maybe plan to do in the future and maybe test it. I am not sure. The way that we implemented this creates some more problems. That's why we have to exchange that key and create a symmetric key so that users don't actually see the content of other users. Right. But I think they should be, with this symmetric key and this cryptography behind, should be in theory similar.
Yeah, and I think this has independent interest just because this also may generalize to other types of systems where you only have a broadcast.
Yeah.
So another question over there.
Hello.
Hello.
Yeah. So thank you for an interesting presentation. I had a master student a year ago who looked at using the IPFS pub sub service for distributing rendezvous points. And that is something that's kind of a similar way of doing the exchange as you have. And I think it's very interesting to use it in different ways. And any things that you can, or any other kind of pub sub services that you're able to test would be great. So which others are you planning on looking into, if any?
So we looked also at the Amazon Pub Sub. The problem with Amazon Pub Sub, which is different from SQS or the way that SQS is implemented, is that there's only, so you can send or publish messages from every device. There's no limitation. However, the downstream channels. So publishers need to be specific endpoints. So like they need to be HTTP websites or sites. They need to be another Amazon service. And there's some other options which I don't quite remember, but it's basically a group of particular options that are not ideal for end users. So for the Amazon pub sub, we would need to create a specific downstream channel different from that service, because that's, or at least leveraging some other service so that we could maybe have end devices be publishers. We also looked at Azure, so the Microsoft Cloud Service. The problem with Microsoft Azure is that they assign specific domains to each service. So like, instead of having this global endpoint, we would have a specific endpoint for our system, which would kind of defeat the purpose. And yeah, I've also looked at, but this was more recently, at the Salesforce pub sub. They also have a pub sub service, and they have a global endpoint, so that might be interesting in the future. And that's basically the cloud providers that we've looked at.
Okay, so I just know that last year the IPFS pub sub service was discontinued as a code. So if anybody here knows about any activity continuing on that, that would be great to know about. Thank you.
Any other questions? No. Okay. Well, let's thank